So I think we can get started. So today we're excited to have Akash from the University of Chicago come. He did his undergraduate degree at the University of Berkeley, where he worked on the CDMS experiment searching for dark matter WIMPs. He then moved on to graduate school at the University of Chicago, where he continued working on dark matter, but switched over to searching for axion-like dark matter with the ADMX experiment. And then more recently, Akash has been working on kind of integrating quantum technology into the search for dark matter, specifically on a paper published in 2021, searching for dark matter using superconducting qubits, which will be the focus of today's talk. And so with that, Akash, we're happy to have you, and you can take it away.
Sounds good. Thank you very much. Thanks for having me, Mike. Yeah. Let me share my screen here. Okay. So yeah, today I'll tell you a little bit about our work, searching for dark matter with superconducting qubits. And I have to thank all the awesome people that I've gotten a chance to work with, including my postdoc, Watson, graduate students, Kevin and Ankur, and my advisors, Aaron and Dave, combination of UChicago and Fermilab here. And just before I get started, I'll pause a few places during the talk so people can ask questions. So feel free to just speak up and ask questions there. I can't really see the chat during the talk, but if someone wanted to read questions out from there during the pauses, that would also be great. Okay, so quick outline here. I'll tell you a little bit about the dark matter that we're interested in looking for and the potential detection mechanisms for those types of dark matter. I'll describe to you why I think we need to build photon counting devices. And I'll tell you about, well, when you build a new device, the protocol that we use to overcome the errors that are inherent to our detector. I'll show you the characterization of this photon counter that we've built, and I'll show you how we use it to conduct a dark matter search. And finally, I'll tell you a little bit about the improvements we've made and are focusing on, and how we think this can be integrated into future experiments. So just the one slide Wikipedia summary of dark matter. We know that dark matter's influence on our universe is evident, especially in the phenomenon such as rotation curves of galaxy. It's imprinted on the CMB. We see it in lensing behavior, as well as sort of the structure of the baryonic matter in the universe today. But we've been unable to detect it so far or study its intrinsic properties. And so today I'll discuss a very specific type of dark matter, but the problem is in general a very interesting one and a big challenge that we're all still working on. So there's lots and lots of candidates for what dark matter is. As Mike mentioned, I worked on CDMS, and so we thought about these weakly interacting massive particles for a while, but more recently I've been thinking about these light dark matter candidates, such as the axion or the hidden photon, and that's sort of what the focus of the talk will be about today. So a quick intro about these light dark matter candidates. The two that I mentioned and I'll be focusing on are the axion and the hidden photon, and here are lots of interesting papers that are sort of just a reference for people to go take a look at if they're interested in more. And the parameter space that describes potential mass of these dark matters on the horizontal axis versus a coupling strength to the electromagnetic fields is here on the vertical axis. And you can see there's lots of white space here, meaning that there's lots of parameter space to still be covered and explored to search for these potential candidates. So what are those detection mechanisms that we can use to try to look for these dark matter candidates? The one that we're focusing on is the coupling between the axion or the hidden photon and the electromagnetic fields. And this interaction is mediated by some coupling. We call it G for the axion, and it's epsilon for the hidden photon. Some people use chi, but this measures the strength of the interaction. And on the other side is the microwave field or a microwave photon. I think about it in terms of photons because later in the talk we'll discuss counting photons. So the mean population that we would expect the axion to produce is very small, maybe 10 to the minus 5. And for the hidden photon, it's maybe a little larger, but we know it's definitely less than population of 10 to the minus 1. So how do we then the problem sort of becomes, how do we look for very small populations of photons? And the first idea is, well, capture these photons in a resonant microwave cavity. And the microwave cavities we build are essentially just the same as the microwave cavities we have at home, except they're made out of shiny metal and they're in these nice polished boxes. So we use copper typically in this work. We'll talk about some aluminum cavities that we use as well. And the key here is that we need to match the resonant frequency of the cavity to the potential mass of the dark matter that we're looking for. And that's sort of one of the drawbacks to this sort of type of search, which is that we know that the signal that we expect to see will scale with the volume, but this scales unfavorably with the frequency of the signal that we're looking for. So as we go to higher and higher frequencies to search for the dark matter, the volume of this cavity will shrink, and the signal of the dark matter that we expect also shrinks. And so this is something that we need to keep in mind when we do our analysis and decide, is this search actually tenable or not? And the way we do make that decision is we need to compare the signal to the potential noise that we have in our measurement chain. So the first technique that we think about when we try to measure the population of the microwave cavity due to the interaction with the dark matter is called linear amplification. And this is where you basically punch a hole into the cavity, put an antenna in there, suck out the power and amplify it. And this effectively is like measuring both the real and imaginary components of the microwave field. The thing to note about this, however, is that we can't measure both of these components with arbitrary accuracy. And this is really just a manifestation of the Heisenberg uncertainty principle. And what this means is that we have an effective noise in units of photons equivalent to about 1. And this is what's called the standard quantum limit. And so, as you can see, as the signal gets smaller and smaller as we increase the search frequency, the standard quantum limit of 1 photon ends up overwhelming the potential signal that we're looking for. And so this search becomes really, really difficult as we go to higher and higher frequencies. And so we've had to think about a different way of potentially measuring the field inside of these microwave cavities in order to enable searches where the signals are extremely small. And the way to do that, we think, is to count photons, to subvert this quantum limit. And the way to think about this is, instead of measuring both the in-phase and out-of-phase quadratures of the field, or the real and imaginary parts of the field, we should measure the signal amplitude only. Of course, you can't beat Heisenberg's uncertainty principle, really. What you're really doing is you're just pushing the penalty of the noise to a different piece of information. And in this case, when we measure the amplitude, we push all of our uncertainty onto the phase information about the field. But for the process of determining if the dark matter has deposited a photon into the cavity, this is completely fine, right? All we care about is there field amplitude inside of this cavity? Knowing information about the phase is not really relevant at this point in time, when we're just trying to detect, was there a photon or no photon? And so the phase-based picture looks something like this. Rather than measuring a blob with some size equivalent related to this quantum limit, you project the state into this ring where you have no information about the phase, but you have very high certainty about the amplitude of the field that you're looking for. Okay, so how do we actually go about building one of these photon counters? So the challenge we have is that we are in the microwave regime, a few gigahertz photons that we're looking for. So photon counters already exist for terahertz photons, things like PMTs or SNSPDs, like I've shown here. The problem is we need low energy counters. And one thing that I'll stress here that we'll get back to is that we actually don't want our measurement to absorb the photon when we measure it. And that's sort of different than this style of detector. And I'll show you how we go about doing that. So here's a schematic for the type of device that we built. And let's take a look at this picture over here. There's really 3 components. One is what I call a storage cavity. And this is where we want the dark matter to accumulate and build up a microwave field. Then we'll use a superconducting transmon qubit that's represented here in purple as the detector of the photons inside of the storage cavity. And finally, we have an auxiliary cavity that we call the readout that we just use to measure the state of the qubit. And just to give some of the details, here are the frequencies, and you can see the relative frequency differences here. And the Hamiltonian that describes the sort of cavity plus qubit system is shown here, where you have a cavity, you have a qubit, and then there's some interaction between the two. And we'll get into the details of all of these. So the cavity part, this isn't really that relevant to this particular talk, but it's just a fun piece of work that I was able to participate in, where we build these really cool aluminum cavities where there are no seams in the cavity. And we can do this by drilling holes from both sides of the cavity to create this larger gap inside that can contain the microwave radiation we want. And we make sure that the holes that we drill are actually too small and too long for that radiation to escape. And this ends up enabling a lot of cool things, such as potentially dark matter experiments, but quantum information experiments as well. The second term in this Hamiltonian is the qubits term, right? And we represent this as a spin here as sigma z. So how do we actually build one of these superconducting qubits? Really, in practice, we know how to make harmonic oscillators. We know how to make inductors. We know how to make capacitors. And so what we do is we really build a harmonic oscillator, and then we add in the one nonlinear element that we have, which is a Josephson junction. And that turns this quadratic potential into a sinusoidal potential. And the key here is that the energy level differences are no longer equally spaced, meaning that the ground to excited transition energy is no longer the same thing as the excited to the next higher order level. And what do one of these qubits look like? So here's sort of the macro picture where the qubit has an antenna on it. And if you zoom in, you can see the Josephson junction that enables this nonlinearity. And the junction is really just two layers of aluminum, as you can see, going horizontally and vertically, and they sandwich a layer of aluminum oxide, which acts as the insulator. So the coupling now, so this is the crucial part and the part that we use to actually build our photon counting device. The way I think about it is really just a dipole coupling between the qubit, which just has an antenna on it that we can engineer and design. So it's this dipole coupling between this qubit antenna and the electric field of the microwave cavity. And when you work out all the math and you account for the fact that we work in this limit where the dipole coupling is actually small relative to the detunings between the qubit and the cavity, you end up with this coupling term here. That consists of an energy scale 2 chi, the A dagger A's representing the cavity population and the sigma Z representing the state of the qubit. And one thing I'd like to stress here is that this 2 chi is something that we can engineer, right? We can go into our design and into the fabrication and actually pick what kind of energy scales that we want here. And I think that's really a really powerful tool in being able to customize these types of devices. So once we have our cavity, we have our qubit, and we've designed the coupling between them, we need to operate this device. And in order to do that, we put that into a dilution refrigerator that's cooled down to about 8 millikelvin. There's two reasons we need to get this cold. The first, obviously, is that we use superconducting materials. And so we need to go below the aluminum TC, the transition temperature for aluminum. But most importantly, remember, we're trying to detect photons that come in very rarely, potentially from the dark matter. And we need to make sure we shut out all other sources of photons, especially the thermal photons that would just be ambient given this giant mass of stuff that's here. And in order to make sure that we shut out these thermal photons, we need to get everything really, really cold. And that's sort of the reason we go to as low a temperature as physically possible. Okay, so let's get into the details here. So on this slide, I've done something interesting where I take the interaction term between the qubit and the cavity, and I group it with the qubit term. And what that results in here is that the qubit transition frequency, everything here in the parentheses in front of the sigma z, is obviously has a component that's its bare frequency, omega q, as I'd written before, but is now also a function of the number of photons A dagger A in the cavity. And we can see that here in the data as well, where we try to measure the qubit transition frequency, but you can see that its transition frequency is in many different places, spaced by 2 chi, and the peaks correspond to there being either 0 photons, 1 photon, or 2 photons in the cavity. And so we've built a coupling that enables the cavity occupation to be imprinted on the transition frequency of the qubit. And this is sort of a useful way to do things because we're really good at measuring frequencies. And so all we need to do to be able to discern between 0 and 1 photons is to measure the frequency of the qubit and check if it's either here or if it's over here. So let me tell you the protocol that we use to actually do that. And it looks something like this. So we'll follow 2 cases, one where there's 0 photons in the cavity, and in the second case, there's 1 photon in the cavity. So we start both of them in the ground state, and that's represented as pointing down on the Bloch sphere here. And we pulse the qubit using one of these pi/2 pulses, and we bring it into the horizontal plane of the Bloch sphere. And you can see that here as pointing along the x-axis. And now we just wait. So remember that the transition frequency of the qubit is different by an amount 2 chi when there's 1 photon relative to when there are 0 photons. And so the qubit, when there's 1 photon, acquires a phase at a rate of 2 chi faster than if there are 0 photons in the cavity. And so if you time this right, you can get the qubit to precess all the way around to the other side of the Bloch sphere when there's 1 photon. And we apply a pi/2 pulse to sort of invert this first one. And what we see here now is that if there are no photons in the cavity, the qubit stays in the same state that it started in. If the cavity contained 1 photon, the qubit state is flipped. And that's sort of the mapping that we do between cavity population and qubit state, using the fact that the qubit frequency is a function of the number of photons in the cavity. Okay, so we put this protocol into action, and we did that by first preparing the cavity with 0 photons, and then preparing the cavity with 1 photon, and then applying this interferometry measurement that I call a parity measurement. And so most of the time when we prepared 0 photons, we measure 0, and when we prepare 1 photon, we measure 1. But as you can see, there are some times where when there were 0 photons, we actually measured 1, or when there's 1 photon, we actually measure 0. And these are really the errors of our detector, right? We're seeing false negatives here, and we're seeing false positives here. And the thing that worries me especially is these false positives, right? A false positive is equivalently like saying, we think we've detected the dark matter when really, in fact, it's just an error of our detector. And that's not something that we want to do. And we think we understand these false positives and these false negatives. It's really that the qubit is in a state that we don't expect it to be in when we're making this measurement. And this is sort of the dominant source of these types of errors. And so we had to think really carefully about what is the protocol that we want to use that mitigates the effect of these types of errors. Maybe I'll pause here for a second if anybody has any more questions. Okay, if not, I'll tell you a little bit about this protocol that we came up with. The way to think about it is to go back and look at the Hamiltonian that describes the qubit and the cavity coupling. And notice that the interaction term here really is just a product of the number operators of A dagger A, the cavity, and the qubit, the sigma z. And so this whole term here actually commutes with the rest of the Hamiltonian. And what this means for us is that when you make a measurement of the cavity state using this interaction, you aren't actually absorbing the photon. You're really just projecting the cavity state back onto its eigenstates of photon numbers here. And we call this a quantum non-demolition interaction. And what that allows us to do is make multiple measurements of the same photon inside of the cavity using this interaction term. And I've displayed the pulse sequence that we use to do that. Here, the cavity is either driven by us or the dark matter, and then we apply this parity interferometry measurement that I described previously with the 2 pi/2 pulses. But then we apply this many, many times, measuring the same photon inside of the cavity repeatedly. So once we figured out that we should actually make many of these measurements, we needed to figure out a way to analyze this measurement record of many repeated measurements. And the intuition here is that we know that the qubit makes errors on the order of, say, 1 to 10%, depending on the qubit that you fabbed, or depending on the environment that we built. But the probability that the qubit will make n repeated errors is extremely small. It's exponential in the number of measurements we made. And that's sort of the effect we're trying to see here. And in order to reconstruct the cavity population, given this measurement record, we had to build this thing called a hidden Markov model that incorporates all of the possible ways in which the qubit can make errors, the way in which the cavity can transition, as well as our understanding of how well we can read out the states of the qubits. And so this hidden Markov model contains things like the qubit and the cavity lifetimes, the spurious population of the qubit, the dephasing rate in the qubit, as well as the fidelity of measuring the ground versus the excited state of the qubit. So once you have your measurement record, once you understand what all the possible transitions of your qubit and your cavity are, you can use this formula here to reconstruct the probability of there being a photon in the cavity. This is kind of an opaque thing to just look at and understand it. So I like to think about a particular example to kind of understand what terms are involved in this formula here. So say we measure a sequence where we see qubit go from the ground state to the excited state. What are sort of all the terms that are involved in this particular sequence? So one way this could happen is there could be a photon in the cavity. The qubit could flip in response to that photon in our parity measurement. And then we could correctly measure that the qubit has gone from the ground to the excited state. The other possibility is that there were no photons in the cavity, but the qubit erroneously flips. This is possible, it happens. And then we obviously correctly measure that the qubit has flipped. The other possibility is that there are no photons, the qubit doesn't flip, but we still make a measurement error. And we measure that the qubit was in the excited state, even though it was really in the ground state. And sort of all of these terms are involved in doing this reconstruction. Knowing the probabilities of all of these things happening is also involved in doing this reconstruction. So let me show you a couple of examples of this in action.
Is the fourth option not also in their calculation?
Which is the fourth option here? Maybe
Photon in the cavity, but the qubit doesn't flip.
I see. So that is also included, but that's a second order error, right? So you're talking about this situation, sort of, where there's a photon in the cavity, but the qubit doesn't flip. That's error number one. But then you also have to make a mistake in your measurement, meaning you measure that the qubit has flipped, even though it hasn't. And that's the only way to see this ground to excited state, this sequence. So that is included. It's just not the first order terms, which is what I've just shown here. Yeah, there are many ways to see the sequence, including where you make multiple errors and they compound on top of each other. Okay, so let's take a look at this reconstruction in action a little bit. So on the left side, I'm showing the measurement record where I basically didn't put any photons in the cavity, and then I made repeated measurements using the qubit. And you can see as I make measurements, the qubit sort of stays in the ground state the whole time, and it's really not in the excited state at all. And then we do this reconstruction using the hidden Markov model, and we see that with very high probability, after say 10 or 20 or 30 measurements, that there were no photons in the cavity because we didn't see the qubit flip. And so this makes sense. It seems like it's working. So in the other case, where we see the qubit flip back and forth many, many times, you can see it going from the ground state to the excited state, ground to excited. Now when we do the reconstruction, after say 20 or 30 measurements, you can see that with very high probability, we think that there is one photon in the cavity. That's these orange dots here. And most importantly, we see that as we make more and more measurements, the probability that there were 0 photons in the cavity, but that this measurement record was actually just a series of errors, that probability is exponentially small. You can see that this is logarithmic on the vertical axis. And so that's sort of built, confirming our intuition here that, the probability that you make many, many errors in a row is very small. And most importantly, we get an exponential suppression of these false positive type events with only a linear increase in the number of measurements we have to make. And so this is a big win for us, right? We don't give up that much, but we get a huge exponential suppression in these false positives. And that's really, really important. So let me now show you how we characterize this photon counting detector. So it's pretty simple. On the horizontal axis, I show the mean injected photon population that we put into the cavity. And on the vertical axis, I show the mean photon population that we measure. And this measurement is really, in each measurement, we do this reconstruction after we make a series of parity measurements, and we ask, was there a photon or not? And we apply some threshold to that. And there are two important components to this plot here. There's a region where we inject a relatively large photon population. And we can see that as we inject more photons, we measure more photons. And we do that with something like a 40% efficiency here. But I think the most important part of this plot here is that as we reduce the number of photons that we inject, we see that rather than continuing to fall off here, this curve sort of flattens out. And this is actually the false positive probability of our detector, right? And this is something like a few times 10 to the minus 4. I think the key here, though, is that we're already sensitive to photon populations that are many, many times smaller than the photon population that you'd expect from the noise of the quantum limit. And I think that's the key advantage of this photon counting detector. And so what we wanted to explore more were, what are these false positives here? And the way we do that is we sort of just go in and look at what all of the events were. We take a look at where we injected a relatively large photon population into the cavity. And in this histogram, I'm plotting the log likelihood of a particular event being either a photon or not a photon. And so when we inject large photon populations, we see that with very high likelihood, we have order of 10 something counts where we think that in fact there was a photon. And this is consistent with the photon population injected. Now, when we reduce the number of photons that we inject into the cavity, we would expect to see almost no events that cross this threshold in likelihood, but we still see a few events. And these are really the backgrounds that we are observing as that false positive probability. And the key here, though, is that we have eliminated the detector errors as a source of these false positives by making these repeated measurements. So what we're really measuring here is a background of real microwave photons that are inside of our cavity. These aren't just spurious qubit flips or readout errors. These are real photons that we see inside of the cavity, and they correspond to having a photon population of something like a few times 10 to the minus 4 inside of our microwave cavity. And I guess for people who are interested, this corresponds to something like a 40 millikelvin temperature that's associated with this. It's uncertain whether these are really thermal photons. It's more likely that they're actually athermal photons, but maybe that's a detail that we can discuss a little bit later. Okay, so what are the implications for this type of counting detector for a dark matter search? And the way I think about it is that if the backgrounds that you're fighting against are small compared to the quantum limit, what you can do is you can integrate for a lot less time. And the way to think about that is that the integration time for any particular dark matter search is the ratio of the backgrounds to the signal squared in terms of rates. And so when you go from using a quantum limited linear amplification technique where the backgrounds correspond to 1 photon's worth of noise versus a counting experiment like this one where the backgrounds are a few times 10 to the minus 4, the integration time is also reduced by a factor of this ratio, about 1,000. And that's a huge win in terms of looking for the dark matter. That means, I don't know, a graduate student potentially finishing their thesis before the end of the world kind of timescales. 1,000 is a huge improvement, and it speeds up the experiment a lot and allows you to explore a larger area in the parameter space in a much quicker time. And I think that's a really big win here. So maybe I'll show you quickly how we actually use this detector to do a dark matter search. One thing I will say is that we don't do an axion search here because we're using all superconducting devices, and we don't want to put a magnetic field on them. So the dark matter search I'll tell you about is a hidden photon dark matter search. And then maybe in the last section, I'll tell you a little bit about how I think this can be adapted and implemented in an axion search. Okay, so what is the actual protocol for doing a dark matter search? The protocol is a little bit different than the standard one where we just amplify the signals. And so what we do is we actually integrate the potential dark matter signal inside of our cavity for the lifetime of the cavity. And then we apply this repeated cavity measurement procedure, 30 times or something, how many ever we do in our experiment. The key here, though, is that while we are measuring the state of the cavity by repeatedly projecting it, we can't integrate dark matter signal because we're projecting the state of the cavity. And this is really just a manifestation of the Zeno effect. And so in our experiment, we do this, say, a few 10,000 times, and that takes us something like 13 seconds to do. And the duty cycle for this is about 65%. You can see that, you can be integrating for some time, but you actually need to wait while you make the measurement. And so this duty cycle is closer to 65% here. We've made quite a few improvements where this is closer to 85%. And so that's really helpful here. And so in this particular work, we did something like 15,000 measurements, and we counted a few photons in these measurements. But we know that these are background events. And so what we wanted to ask is, based on this observation, what hidden photon mixing angle in the parameter space is excluded? Meaning, if there was a hidden photon dark matter candidate that would have produced much more than these photons that we counted, well, we would have seen that, and we can exclude them because we did see that. And that's sort of the logic here. And when we put it all together, this is sort of the constraint we're able to make on the hidden photon dark matter. You can see that the constraint is most severe on resonance with the microwave cavity, and we have these fringes that are associated with the particular details of the measurement that we're doing. And the hidden photon mixing angle parameter epsilon that we're able to exclude is a few times 10 to the minus 15. And you can see that this actually doesn't go all the way to the top. So this strategy is actually very complementary to all sorts of other types of experiments. And I think the key here is that we're able to do this very, very quickly using our photon counting technique. And so even though this is extremely narrow, we think that we can tune this exclusion over large regions of parameter space just by the traditional techniques of tuning our cavity. And one of the coolest things I think is that the qubit and the cavity interaction is already designed to be off resonant. And so even if you move the cavity around a little bit, it doesn't actually change the fundamental interaction between the two. And the search can continue just as previously described. Okay. So, this is kind of a fun story. We basically warmed up our fridge and then we cooled it back down. And then we took a lot more data. We improved on the microwave lines. We improved the optimization of the pulses. And we get up to higher duty cycles. But just because of the thermal cycling, the cavity frequency actually changed a little bit. And so we were able to do a slightly different exclusion. Just sort of a detail here. Okay, So what are the improvements that we've been making and that I think we should be making, and sort of the future experiments and the future outlook for this type of work? So I think the most glaring thing that we need to improve upon is understanding these background photon sources and figuring out ways to mitigate them. So there are lots of ideas about what this is. The first one is, well, your lines inside of your dilution refrigerator are just leaky in the microwave domain. And so we need to think about more attenuation or better attenuation and filtering, as well as improved thermalization of all of the components that go inside of the dilution refrigerator. The other thing that people have recently found is that we actually see the effect of radiation, terrestrial or cosmogenic, and high frequency photons that come in and sort of spuriously change the state of the qubit. And one of the key insights that we've been thinking about is that, well, the qubit and the cavity are actually coupled to each other. So even if you excite the qubit, with some smaller probability, we can actually excite the cavity. And so all of these mechanisms by which the qubit gets excited are also sources of potentially photons being present inside of the microwave cavity. And some of the ways we think we can combat these spurious qubit excitations that then lead to photon excitations are device related, like engineering the superconducting gap of the materials that we choose here in our qubit. We can put traps for quasi-particles that are the source of these sorts of excitations, as well as potentially using different materials like tantalum and niobium and things like that. There are probably lots of other sources of these types of background events, and we just haven't accounted for them yet. And so it's still really an open question where we still need to understand these things. And I think just working with a diverse set of scientists, I think, will help us understand what all these sources are potentially. My quick estimate of what I think we can do is we can get our backgrounds from a few times 10 to the minus 4, just doing all of these simple things, down to at least a few times 10 to the minus 5, which corresponds to something like 100,000 times search speed up relative to a quantum limited search. And so this is sort of an estimate of what I think we can do. Okay. Some of the other fun ideas we've been thinking about that aren't really related to photon counting are, well, we thought a lot about how to reduce the noise in our detection mechanism. But the other thing that we can think about using these quantum techniques is how do we actually enhance the signal of the dark matter? One of the simplest ways is, well, you can build a high Q cavity that'll help accumulate a larger signal inside of your cavity. And we want to make sure that this cavity is also compatible with magnetic fields, so we can do not just a hidden photon search, but an axion search. And so Ankur has been working a lot on these photonic bandgap cavities that are made out of concentric layers of dielectric materials that are spaced in a specific way to make sure that radiation doesn't leak out. And we think we can get Qs of 1 to 10 million potentially using these techniques. The other thing that I'm very interested in is what happens when you don't start your cavity in its ground state, and instead you start it in some sort of non-classical state? Can that be used as a way to enhance the probability that the dark matter deposits a photon? And we think the answer is yes. The simplest way to think about this is, say you start your cavity with exactly n photons. So this is a Fock state that contains n photons. You can think of the dark matter as sort of a displacement on that. It's a very weak displacement. And usually, typically, we start this in n equals 0. That's just the ground state, and we look for a small displacement of the cavity. But say you started it in n equals 5 or n equals 10. What happens? Well, we look at what happens at n plus 1. And we can see that the probability of measuring a photon is no longer just alpha squared, which is what you would expect if you started in the ground state, but really it scales as the Fock state number that you started in times alpha squared. And we've already demonstrated that you can make these Fock states inside of the cavity using their coupling to the qubit, and we're working on showing that this enhancement is really possible. Okay, some of the other things that we've been thinking about is, well, one thing I found is that tuning things mechanically is very difficult. And so we've been experimenting with potentially electronically tuning one of these cavities. Of course, this is very difficult inside of a magnetic field, and so this is solely reserved for a hidden photon search. But what we're doing here is we have our storage cavity here, we have our readout cavity here, and we have a qubit that's doing the same photon counting procedure. But we have this additional element that's really just a tunable resonator. And what we can do is we can sweep it in and out of resonance with the storage cavity. And as they cross each other, you get this avoided crossing that actually tunes the storage cavity. And we think we can get orders of 100 megahertz of tuning, which correspond to 5 to 10% of tuning, which is pretty significant. And so this device, as you can see, is constructed, and we're sort of mounting it and trying to test it at the moment. And the next biggest question is, well, how do you integrate all of these techniques into an axion dark matter search? And this is sort of where I'm making a pitch and an advertisement for the people who are interested in this and want to work on these kinds of topics. The parts that we understand are over here on the right, where we have our qubits, we have our storage cavity, we can count photons, and then we kind of understand what's going on over here on the left. So we can make relatively high Q cavities inside of a magnetic field. But how do you bridge these two things and connect them? And we have some ideas about using waveguides and some sort of nonlinear elements to do swaps of the states of the cavity over here in the magnetic field into the storage cavity. But this is still an open question. And we have a few people thinking about this. And I encourage other people who are interested to get started thinking about this, and because I think this is where sort of the next big challenge lies in making this a full-fledged axion dark matter experiment. Okay, and with that, I think I'll conclude. I think I've had a really great time sort of using these quantum information techniques and devices, but in the context of a dark matter experiment. And the key takeaway, I think, is that we've achieved something like 15.7 dB of metrological gain, which in terms of a dark matter experiment corresponds to speeding it up by a factor of 1300 relative to the quantum limit. And we've shown that with this speed up, we're able to quickly achieve sensitivity to the hidden photon dark matter in an interesting regime. And of course, the details are all in this paper, and I'm definitely happy to answer more questions that people may have. So with that, I think I will stop and open it up for discussion. Thank you all very much.
Thank you, Akash. It was an excellent talk. So with that, I guess we can start opening up for questions. Okay, looks like Shamita, your hand is raised.
Hello. Great talk. Thank you so much. I have two questions. One is, so you said that the qubit cavity interaction is inherently quantum non-demolition, and I want to know if that's because they're necessarily detuned, or if it would still be quantum non-demolition if the cavity and the qubit were exactly at the same frequency.
That is a good question. Basically, the answer is that they have to be detuned.
Okay.
So you can see that the interaction is really some complicated mess of ladder operators. And it only simplifies to this product of number operators when you're in this detuned limit.
Okay.
Right? It's really just an exchange interaction when you're on resonance.
Okay, that makes sense. And then thank you. And then my second question is, can you go back to the electronic tuning of the cavity and give some more details about that? Because that's cool. I didn't know about that.
Yeah, it's actually pretty simple, right? Like if you take two microwave cavities and you somehow on a piece of paper, you can tune one of them. You can sort of bring them in resonance and out of resonance from each other. And if they have some sort of coupling with each other, either basically via electric fields, you can get them to avoid, get this avoided crossing, basically where they mix, they hybridize when they're on resonance. And that's exactly what's going on here. So this, instead of another microwave cavity, we're using a an LC circuit, but we're putting a tunable L in there using Josephson junctions.
Okay.
And using this tunable inductance, we can sort of move the resonance of one of these around, and we can use it to cross the resonance of the fixed storage cavity. But it's not really fixed anymore because it's coupled to this tunable thing. And so you can see that, when you're far away from them, you have two separate resonances, but as you tune one of them and it gets closer and closer to the resonance of the other, you get this avoided crossing. But that really just means you have this sort of this tuning of one of them or this one. Of course, one of the drawbacks here is that on resonance, they're maximally mixed together, meaning that the wave function of this combined state really lives half in this cavity and half in this LC resonator. And so the form factor is degraded by a little bit, but we think it's not so bad. That's sort of this plot here, where the form factor is degraded by about close to a factor of a half, essentially right on resonance of what you would expect in just an empty cavity. And so maybe that's a sacrifice we're willing to take for this amount of tuning.
Yeah. Thank you very much.
Yeah, of course.
And great talk again.
Thanks.
Okay, looks like Yuki, you have your hand raised.
Right, thank you. Hi Akash, it's really cool. I learned a lot. I will limit my questions to two. My first question is regarding your, I guess, background characterization at around, I think, page 15 or so. So you mentioned that when you're characterizing the background, you're basically preparing the state of the cavity to 0 and 1 and the measure. So and then you introduce the hidden Markov model to understand the false positives. So
Yeah.
I was wondering, when you were preparing it and doing this, in the case, I guess you don't actually have, you don't actually need to worry about thermal photons in this case. Do you include like the false excitation, false positives due to thermal black body photons in your hidden Markovian? It wasn't quite clear to me if you.
Yeah, they are, but effectively what happens is it's sort of this iteration where we don't know what the heating probability is, because that's effectively what we end up measuring, right? The probability of a thermal photon in our cavity is really this number, right? Because this is the measured photons that we count in our cavity when we don't inject anything. And so what I do is I actually then take this and I feed it back into the hidden Markov model and then rerun the analysis, and it basically says the same thing.
Okay, but I think at some point you mentioned your cavity is at 8 millikelvin, but this number you said corresponds to 14 millikelvin.
Absolutely, yeah. That's one of the biggest, starkest differences that we see, right? The physical temperature of our cavity is 8 millikelvin, and we expect the thermal temperature, the photon temperature to also be 8 millikelvin. But what we actually find is that it's not, it's at 40 millikelvin. And sort of, we don't know exactly why. We have a few of these ideas. Leaky microwave lines, weird excitations due to coupling to the qubit. But this is still an open question that's very important for the dark matter community, because we're looking for very small signals, but also I think becoming more and more important for the quantum information community.
Yes, so when you mentioned the possibility of false positive, you said that it could be the qubit. I was thinking of it, is it kind of like a spontaneous decay of the qubit into other states due to coupling scheme? So are they definitely excited by photons, or there are other mechanism that doesn't require coupling to photon that would lead them to decay into a different state, but that will lead to false positive? I guess my question is there like any other mechanism than coupling to photon that can lead to false positives when it comes to qubit?
Oh, you mean in terms of why the qubits make errors? Or are you
Yeah,
talking
okay,
about
so my understanding is that at some point you are saying in your hidden Markovian model, you're accounting false positive due to qubit error. So
yeah, exactly.
My understanding was that was not the thermal photon that you're accounting for. That was something else.
That's exactly right. Yeah.
Okay.
That's exactly right. So we know that the qubits spuriously get excited. People again have ideas for why that is. But that's something that we can measure pretty easily and calibrate. And those numbers go into our hidden Markov model. What we don't know is what is the thermal population of the cavity itself. And that's exactly what we end up measuring in the end. The residual photons that we see inside of the cavity, we attribute them to the thermal photons. And then we say, well, this is not thermalized. The photon temperature is not the physical temperature. And that's something that we need to work on.
Okay, thank you.
Yeah, of course.
Okay, I think the next hand raised I see is Shirin.
Yeah, thank you for the talk. First of all, it's a good talk. And my question is, so you said this scheme can speed up the search by a factor of 1,000, like 1,300. Just wondering at what frequency regime this speed up applies to. Is it only works at high frequency? And also this question kind of tied to, I'm just wondering, like, because you say when you perform quantum non-demolition measurement, you have to be in detuning regime, but when you're changing the frequency, where you're like stepping through the frequency space, how do you keep this detuning? And then when you do that, if there is a limit, so that this speed up doesn't apply.
Yeah, that's a great question. So as you can see, we are sort of in the few gigahertz regime. And basically where I think this speed up really works is where the noise associated with the standard quantum limit overwhelms your signal, right? Like if you're already in a signal dominated regime, you don't need to worry about any of this, right? And so that crossover happens, I don't know, maybe a gigahertz, maybe somewhere around there. And that's sort of where I think these counting techniques really become powerful, or some non-classical detection technique becomes powerful. In regards to the second question, you can see that the qubit and the storage cavity are already over a gigahertz detuned from each other. And so I would say that even about 500 megahertz of tuning on a let's say 600 megahertz of tuning in either direction on a 6 gigahertz cavity is totally feasible. We've made cavities and qubits be like 200 or 300 megahertz detuned from each other and still have quantum non-demolition interactions. And so I think you can get something like 10 to 20% tuning. I mean, assuming you know how to tune the storage cavity, which one of the ways is the traditional technique of putting a rod in it around. Whether or not you can actually use one rod to move it by 600 megahertz, I don't know. But I think that doesn't affect your ability to do these quantum non-demolition operations. Especially because these detunings are already huge. And so even a 10 or 20% change of one of these frequencies doesn't affect that interaction very much.
Right, and your qubit in principle can also be in a different frequency if needed.
Yeah, so that's right. I would say the qubits can probably be from anywhere like 3 to, this top range is maybe not so concrete, but maybe 15, maybe 20 gigahertz. Unknown. I don't know if anyone has made a superconducting qubit like this at 20 gigahertz yet, but I still think it's possible. I think the highest one I've made is about 15 gigahertz.
Cool. All right. Thank you.
Thanks.
Okay. Looks like the next hand I see is from Steve.
Yeah. I like your cavity. I wish it was tunable.
Me too.
There's it's a big problem with all of this is making the detector aspect of that you couple the cavity, making that tunable.
Yeah.
And you talked about that. And one thing I'd like to mention is this business of the dielectrics in a cavity. We're working on this right now, but that pretty much steals a lot of your signal, and exactly how much is a point of debate. And I think it's actually pretty significant. The role of the cavity for the dark matter conversion is an impedance matching device. And although the Q goes up, the impedance goes way down. So the conversion of axions to an electric field goes down. Anyway, I don't want to go into the details, but
do I think about that as like a reduction in the form factor, just because you're occupying so much of the magnetic volume, but your cavity is really confined to this
that's
very
right.
small defect?
Yeah, it's all electric storage. There's no magnetic storage of the system.
I see.
And so you need both of them to convert the axion. And once you have a
Right.
lot of dielectric, it just kills the magnetic part of it. And
I see.
so, you know, we've been arguing about that for years. And I had to referee one of the Korean groups. There's two competing groups in Korea doing this, and got a dielectric rod. And I said, you know, the effect of that rod is really big. And they said, no, it isn't. And I said, well, yes, it is. And then I made an estimate, and it was on the low side, and they did it. And they said that the effect's even bigger than I said. So maybe, you know, it's just something to pay attention to.
Yeah,
and,
for sure. That's a good point.
Yeah. So, you know, the real one thing with this temperature, you know, when in our cavity, we have this, what we call the hot rod effect. We've always assumed it's a tuning rod, not cooling down.
Yeah.
But we cool down to 60 millikelvin. Our system temperature is always about 100, sometimes much higher. What was it most recently, Mike? Was like 150 millikelvin when it was really working right.
Yeah.
And, you know, somehow we never can get below that. And we've always thought it's the tuning rod not being coupled efficiently, but I kind of wonder if there's some other physics going on. You know, you're getting 40 millikelvin. You have a nice tiny cavity, really well heat sunk, and
we also pay attention very closely to the microwave lines. Like I mean, we built this specifically to make this cold.
Yeah.
Right?
So, you know, where's this extra energy coming from? That's really one of the big questions now. And, you know, is it hot electrons? And one problem is, you know, we always have these low noise factory amplifiers, whatever, for the final output stage.
Right.
Well, they have a reverse output too. You know, there's a coupling from the output back to the input.
Yep.
And, you know, there's always isolators and circulators and all that, but you know, if you have 20 dB, that's already down to 40 millikelvin of noise, and it's, you know, that's a backward directed signal. And is that charging up your cavity? I don't know. We tried to play around with that by, you know, looking at the cavity temperature as a function of the antenna insertion and stuff like that. We didn't really see any effect, but that's a tricky measurement, because when you pull it out, the coupling into the cavity goes down, so the voltage at the end of the line goes up. So it's not so clear that you're really measuring what you think you're measuring. Anyway, I just throw that out because this is an unsolved problem, and you know,
I totally agree. Yeah, this cavity was iterated with fridge cycling about 15 times, where we changed one component in each cycle, where we, you know, took like one layer of the shield off of the last circulator, like added an echosorb filter right after the cavity from the line, from the output line. And it really took a lot of work to get even down to 40 millikelvin. And I would say there is no silver bullet. It's really like combination of a lot of these little things that sort of just add up. And even 40 millikelvin is too hot, right? It should be at 8 millikelvin. And so there's still a lot of way to go. I think one of the best things about this though is like the population is exponential in the temperature. So like 20 millikelvin is exponentially better than 40 millikelvin, of course. And so even a few millikelvin here and there really makes a big difference, I think, for these types of experiments.
Still, it's such a vexing problem. You know, you have the thing, it's a hunk of metal. It should be at 8 millikelvin.
Should be cold, absolutely.
And, you know, there's this whole, we've been talking about, you know, hydrogen being stuck in there in the, you know, in some excited state. And I think that's far-fetched. And the fact that you're seeing this effect with your cavity really tied strongly means that our hot rod problem is likely something else. Anyway, I just throw that out as something interesting.
Yeah, that is very interesting. Thanks.
All right. The next hand I see up is Yiki Wang. Sorry if I said that incorrectly.
Hi, can you hear me?
Yeah.
Yes.
Thanks for your talk. It's a very great talk. So I have two questions. First question is that what's your motivation to use a cavity to couple to the dark matter? If it's not a microwave cavity, can I use, for example, mechanical resonator, for example, to couple to the dark matter?
Oh, that's Interesting. Maybe. So that would be sort of testing a different hypothesis than the one that we are testing, right? We're specifically testing for this coupling between the dark matter and the microwave and the electromagnetic fields. I know that there are other potential couplings for these types of dark matters, and like via, well, yeah. So yeah, there are other types of coupling. I don't know how you would get coupling to a mechanical resonator, though. That's something I'm not sure about. Yeah, I'm not sure, because we're specifically looking for these microwave photons, right? It just happens that a microwave cavity is the best way to hold a microwave photon. But somehow if you wanted to transduce a microwave photon into a mechanical phonon, that may be a nice way to do things as well. Just because maybe mechanics maybe have higher Qs, and so you can store them a little longer or something like that. That would be cool. But we just do the simplest thing, which is we think a photon's coming out, so we catch it inside of a cavity.
Next question is that I see you are using the information of the count to interpret how many photons in your microwave cavity. Have you ever think about using other statistical properties of counting? Other properties.
Sorry, I missed that last part of the question.
So have you ever thinking of using other properties of statistics of the countings rather than just the count rate itself to interpret how many photon or that one photon state or whatever state in the microwave cavity?
So sorry, do you mean like counting 2 photons or 3 photons, or do you mean like well, I guess yeah, that's what it would be, right? Yeah. Then you would potentially get different statistics.
Photons, for example, correlation between photons.
Yeah, to measure the correlation between. Yeah, absolutely. So in this work, we don't do that because we can only measure 0 or 1 photons. But it's not that far-fetched of a thing to do, because as you can see from this plot here, our qubit is sensitive to 2 photons. In fact, there is a 3 photon bump here, but we've measured these spectra all the way out to like 20 photons. And so if you wanted to ask the question, what's the probability that a 20 photon event happened, you would be able to do that with a qubit, right? Well, we just didn't happen to do it here. We think that it's unlikely with the dark matter, just because we think it's a coherent drive, and we think, but that does mean that there is some probability of 2 photons. It just means that it's exponentially smaller than the 1 photon case. And so we don't really think about this one, but it's true that it's a possibility. And one of the things I've been thinking about is like our backgrounds, we don't think that they are thermal, or even if they are thermal, we should measure the full distribution. Like how many, what's the 1 photon probability, what's the 2 photon probability? And so that'd be something interesting to do. And we do have the capability of doing it. So that's a good suggestion, a good thing to think about for trying to characterize the statistics of the background, right?
Yeah. Maybe the last question is that what's the detection efficiency of your photon counters?
It's about 40%. And I think maybe with some improvements we've made recently, we have something like 60% or something. And this is really because we bias this detector in a regime where we're trying to minimize the false positives as much as possible, right? And so we throw away a lot of events that potentially are real photons just because we think, okay, maybe this could have been from a few errors. And so we actually throw away a lot of events. If I put this at a threshold of 1, meaning that like the probability of an event being a photon is just a little bit greater than it not being the photon, our efficiency is closer to like 95% or something like that. But we don't want to operate in that regime. We want to operate in the regime where the false positive probability is as small as possible.
Is this efficiency sensitive to which optical which microwave mode is excited?
It will be, yes. We only work with the lowest order mode of this cavity, though. And we do design other cavities where we work with order of 10 to 15 modes at a time, all coupled to the same qubit. And in that case, we do see efficiencies that are a little different, but probably not that different, because the false positives we think that we're suppressing are really all from the qubit, right? Qubit makes an error, or you have a readout of the qubit that's erroneous. And so it doesn't really matter which mode the qubit is coupled to very much. The qubit will still make errors at the same rate. And in fact, in those multimodal cavities, we couple it to all the modes at the same time. And so in that case, I don't think it very much matters which mode you're interrogating. Of course, the coupling of the dark matter to that particular mode may be different. And so that's sort of where another factor of efficiency may take place.
Thank you. Thanks again for your great talk.
Thanks very much.
Okay, yeah. Thanks for the talk, Akash. It was it's past 2 p.m., so your time commitment to us is